Right, so last time we were starting to investigate the dual space of little c0. We got quite a long way. We were looking for an isometric linear isomorphism from little L1 to the dual space of c0. And let's see how far we got. We had, for every element of little L1, we had come up with a corresponding continuous linear functional on c0. So what did we do? We took y in L1, which was yn, and we used that to define what we called phi sub y, which was defined by what it did to an element of c0, x equals xn. It took it to be the sum from n equals 1 to infinity of xm yn. And it turned out that then this phi y defined a continuous linear functional on little c0. And we had that the norm of that continuous linear functional was at most the one norm of y. So that's what we had to start with. So we knew then that the operator norm of this bounded linear functional was at least the operator norm of y, at most the operator norm of y. However, we wanted it to be an isometric linear isomorphism, so first we wanted to check that you got equality, so we needed the inequality the other way around, that the operator norm was at least the norm of y, and that was okay. And then we wanted to make sure that every bounded linear functional on C0, every c in C0 star was one of these phi y's, and then we'd be finished. So we did the norm inequality, and so we established that the operator norm of phi y was correct, but what we hadn't yet done was show that every element, every c in C0 star was one of these. Now, we're going to need a little aside here to finish this off, because here's something that we need to know about. I didn't tell you about the standard unit vectors in these spaces. There's a slight irritation on the notation, but I think I will have to go with the standard notation on this. So, standard unit vectors En in the LP spaces, etc. What are they? Well, this doesn't fit with our previous notation, unfortunately, but since everybody always calls these En like this, we're going to have to stick with this. En is a sequence. En is in C00, and En is equal to the sequence which is 0, 0, 0, 1 in the nth place, and then 0 again. Or in other words, En is equal to the following sequence: delta nk, k runs from 1 to infinity, where this is the usual Kronecker delta symbol. So it would fit better with our previous notation if we had written E upper n, because this is a sequence of sequences, and there's one for each n. So you could say En equals En is in C00. And it's just unfortunate with the notation. But note that the norm of this in any of the spaces we've looked at is 1 so far. So note that norm En infinity is 1, and norm En in any of the p norms is still 1 for 1 small root of p smaller than infinity as well, because there's just one term which is 1, you add it up and you get 1, and then you take the p root and you get 1. Are people clear that En is actually an element of one of these sequence spaces and not a real number? In our previous notation, normally if we had the n at the bottom, then it would have been a real or complex number. But this is an exception for the standard unit basis, because everybody writes it this way. Any questions about these standard unit vectors? Well, so that's the... I'll just note a little bit more about that before we go back to the proof of the result we were in the middle of. You have the linear span of these. These actually form a Hamel basis for C00. So E1, E2, E3 is a Hamel basis for C00. In particular, C00 is the linear span of these. This is rather easy to check. And again, if you're thinking of C00 as being the same as the polynomials, then these ENs are the usual monomials. If you think of C00 as being something like the polynomials, though you might want to allow a 0th term for the constant, I guess, then these would be the monomials, things like x to the power n. Right, okay, so now, if you want to check that two bounded linear functionals are equal, and you know that C00 is dense in your space, you only have to check that the linear functionals are equal on C00, and the rest will follow from continuity. So let's have a look at this. Back to the proof. So let psi be in C0 star. So it's a bounded linear functional on C0. We need to show that there exists a y in L1 with psi equals phi sub y. Now, it's a bit irritating, because in the middle of this, we end up proving something pretty much proving again something we've already done. And that means that there is a more efficient proof structure, but you have to be careful. Okay, so let's say how you do this. Look at C of En. En, regarding En, where En is in, thinking of it as being in C0, okay? Then this gives us a sequence of values which will do what we expect to happen. I mean, if you look at what phi y does to the En, it picks out the element Yn. So this should be what Yn should be. So we set Yn equals psi of En, which is of course in F, and you set y equals Yn, and so far that's just a sequence. And now we need to prove that y is in little L1, and the rest is then quite easy. So what have we done? We've taken our psi, and we've seen what it does to En. And if psi is going to be a phi sub y of something, then psi of En has got to be Yn. So this is the only possibility if it's going to work. Now we've got to show it works. So this is as before. Choose some scalars alpha n. With mod alpha n equals 1, such that alpha n yn equals mod yn, just as before. And now let's again have a look at what does C do to the sequence alpha 1 up to alpha n and stop. C of the sequence alpha 1, alpha 2 up to alpha n. Sorry, that has to carry on. 0, 0, 0. But that's just a nice linear combination of the e's. That's C of sum from k equals 1 up to n of alpha k ek. So that being a finite linear combination, we can just write that as the sum from k equals 1 to n of alpha k psi of ek, which is sum from k equals 1 to n of alpha k yk, which is equal to the sum from k equals 1 to n of mod yk, because that's how the alphas were chosen. However, what about this element alpha 1 up to alpha n? Remember, this is very similar to what we did before. What is the norm of that in C0, the norm infinity of that element of C0? So that's just going to be the supreme of the modulus of the terms here. And they're all chosen to have modulus 1. So the answer is 1. So, psi of it, the most that psi of it can be in modulus. I should have given it a name, really. I wish I'd given it a name now. The most that can be is going to be the operator norm of psi, which is finite, of course. Where have I got my extra brackets? Oh, something is wrong, yes. It's a question of whether my notation for sequences, whether or not I put brackets around them or not. Anyway, so what we've got here, we've got most of the operator norm of psi, but so this sum then is at most the operator norm of psi. Now you let n tend to infinity. To obtain the sum from k equals 1 to infinity of mod yk is finite. And you've pretty much reproved the relationship between the norms as well. And yet, there's a subtle difference between what you did this time and what you did last time. So, obviously, there's a lack of economy here, and you can combine those two steps, but only if you're careful. So that means that that sequence yn, n equals 1 to infinity, is in little L1. And finally, note that phi sub y of En is also equal to Yn, because En has just got a 1 in the nth place. The phi sub y means you look at the sum of the xn yns. When the xn's are just 1 in the nth place, that picks out Yn. But that's the same as psi of En. So, phi y and c agree on E1, E2, and so on. But that means they agree on the linear span too, because these are linear functionals, so they must agree on the linear span. The linear span of those, which is C00, 0. So they're equal on C00, 0, but they're continuous, and C00 is dense. When two continuous maps agree on a dense subspace, they must be equal. And we finished at last. Okay, I invite you to investigate making a more efficient proof. There are some alternative proof structures available in the written notes that I did from 2006 to 7. So if you go back to the 2006 to 7 notes, I did this one this way, and I did little L2 the other way, the more efficient way. It's just that there are some subtle things to watch out for, and so I usually do. I normally do one of them the slow way and one of them the fast way. Yes?
You said because it is dense.
Yes.
And because they agree on this, then,
Yes.
Then they are equal.
Because they're continuous as well. The set of points.
They were different at some point, and because they are continuous, we have like
a little open set. Yeah. So if two continuous functions disagree, there'll be a little open place where they disagree, but that will contradict the denseness. Alternatively, you can say that the set of points where the two continuous functions agree is closed and includes the dense subset. And any closed set that includes the dense subset must be the whole thing. So you can either go for the open set and meeting the dense set, or you can go for the where they agree is closed. And so you can take limits of sequences on both sides. So any point in your space is the limit of a sequence from your dense subset, and then you can take the limit of the values, which will be the same. Several different ways to finish it. But at this point, we can just say, you can quote that if two continuous functions agree on a dense subset, then they must be equal. But I can leave it an exercise for you to check that. Agree meaning having the same values. Okay, so that's the C0 star is little L1. Now, there's L1 star is little L infinity. That's on the question sheet. So you get to do that one. So that's an exercise. You can just imitate this proof and you'll find it works pretty much the same. And then there's L2 star being L2, which is like a Hilbert space result. So if you know Hilbert spaces, you can get that for free. And then there's little LP star being a little LQ for a conjugate index, of which the little L2 is a special case. So let me go on and say something about these little LP spaces, though we won't be able to prove everything in full detail. So what do we have? So here's how the conjugate indices work. If 1 is less than p is less than infinity, then 1 over p will be less than 1. And of course it's greater than 0. And then the same is true. So you've got 0 less than 1 over p is less than 1. So 0 is less than 1 minus 1 over p is less than 1 as well, because you just subtract from 1 and it's still true. And this is 1 over q. So q is equal to 1 over that. You can actually simplify that, but I won't bother. Now, special case of interest is when p equals 2. 1 over p is a half, and you get q equals 2, 1 over q is a half. And again, 1 over p plus 1 over q equals 1. The conjugate index is going to tell you which space is going to be the dual of your space. Now, you could almost think of the 0, 1 and infinities as being special cases of these, just about. Obviously, that's not quite valid. 1 over 0 is going to be horrible. So you don't really want that. 1 over, so I don't mean 0, but there's 1 over 1 and 1 over infinity as just about working. So that wouldn't be a very rigorous approach, but it does explain why maybe you'd expect little L1 star to be little L infinity. And I guess that doesn't fit for little c0. So here is the result, and it's all based on Hölder's inequality, and you can find all details in Rudin's book on real and complex analysis, but here's what happens. You do your conjugate indices, you take p and q strictly between 1 and infinity, then LP star is LQ and LQ star is LP, and although I won't prove it for you, I will show you what's going on, because it also covers the little L2 case, just to explain again what you would do and to see where the issues come in. It's exactly the same system. So this is a sketch of the proof. And note that p equals 2, q equals 2 is a special case. And it's very like the proofs we've already done. So it's similar to above. For y equals yn, n equals 1 to infinity in little LQ, you attempt to define, or we try to define, phi y in LP star by phi y of xn is the sum of xn yn as before. Now it turns out that if y is in LP and x is in LQ, then this works. And moreover, Hord's inequality tells you the following. So, optional reading exercise to find out about Hord's inequality. Sum from n equals 1 to infinity of mod xn mod yn is less than or equal to norm xp, norm yq. It's finite. And it's less than or equal to norm xp, norm yq. Which in particular is finite. So this does make sense. Notice that when p equals q equals 2, this is just Cauchy-Schwarz. So you can think of Hord's inequality as being a generalization of Cauchy-Schwarz, which works with conjugate indices. And of course, it's more general than this. It works in measure spaces as well. So it's quite general, Hord's inequality. But this is one version of Hord's inequality. So this is a good start. So it follows that Vy is in LP star, and that the operator norm is less root to norm yq. And the rest of the proof is to show that you get equality there, and to show that every continuous linear functional LP has this form. And it's very similar to before, but there's a neat trick in the middle, which I won't go into. So the rest is similar to before. You still have to use Hord's inequality again. Show that norm Vy op is greater or equal to norm yq, and that every C in LP star is equal to Vy for some y in LQ. And of course, you find it the same way. We're not doing the details here. But given C in LP star, of course, the y you need is given by yn equals psi of en again. So yet again, if you've got some bounded linear functional and you want to find a y that does the right thing, you know what it has to do to the ens. So you look at psi of en, that gives you yn. That's given by yn equals psi of en. And the rest is lots of little technical calculations using Hord's inequality. Not very difficult, but just a bit beyond what we're going to do. So that's after all, it's an incomplete proof. It's also a non-examinable proof. That little one I just did there, because it's incomplete. I just wanted you to see how the same sort of idea works. you could be asked to do some little sub-calculations. But what you are supposed to do is you're supposed to know these results about what is the dual space of each of these spaces. So you're supposed to know that the dual of C0 is little L1, and you're supposed to know how to prove it. And it's an exercise on a question sheet that the dual of little L1 is L infinity. So it might be a good idea to know how to prove it because it's a question sheet question. The dual of little L2 being little L2 is, I've only told you, indicated a sketch of it here. So it's a non-examinable proof this year for little L2. But nevertheless, you could be asked to do some little sub-calculations of it. Right. So the rest of this subsection is an optional reading exercise. I want to say something about it because it does fit and maybe motivate a bit some of the measure theory stuff I've handed out. Now you'd have to read up on this in real and complex analysis to know what's going on. But those of you who did do the measure and integration module will know that if you've got a measure, you can integrate against it and so on. And you get these spaces, big L1 being the sort of integrable functions. L infinity is a technical definition you need to look up. But in the special case of counting measure on the natural numbers, this just comes down to the ones we already know. So if you use a counting measure on the natural numbers, these big L1 of mu's are just the little LP spaces. And so what happens is that our results for little LP are the special cases where mu is counting measure on the natural numbers. Which means that the size of a set is how many points the set has got. Naught, finite number, or infinity. So you may want to find out about that to just get you a little bit more information about and a bit more motivation on how this stuff works. Okay, that's the general version of the LP spaces. Then there's the Riesz representation theorem. Not the same as the Riesz-Fisher theorem for Hilbert spaces. This Riesz representation theorem is about what is the dual space of the continuous functions. Here's continuous complex valued functions on X. Well, turns out that every bounded linear functional on the continuous complex valued functions is given by integration against some measure. So we already have seen some special cases where you integrate functions, say, over an interval against normal Lebesgue measure or something, and or just Riemann integration of a continuous function over an interval, giving you an example of a linear functional. That was on sort of the first question sheet. Well, in the abstract setting, if you want to know what all the bounded linear functionals are on the C of X, then it's given by integration against measures. There's even a bit more information. You can say how big the measure is. The so-called total variation of the measure is the same as the operator norm of the linear functional. So you can find out all about this stuff in Rudin's real and complex analysis. And you get measures that represent your linear functional. And the same, if you work with real valued continuous functions, then you need a real measure. And I guess probably the best thing I can do is ask, are there any questions on the material in that section? Anything I could say a bit more about? The next section, 3.8, is all about bounded linear functionals and extending them from subspaces to bigger spaces. And we won't have time again to go through all the details of the proofs because we'll just have to discuss the results and I'll explain the consequences. And one of the consequences of the main result in the next section is the Hahn-Banach theorem, and we'll be explaining that and how it works. And one consequence of that is that there are lots of bounded linear functionals in a perfectly general setting, and one of the main results we will get is the existence of support functionals. So section 3.8, let X be a normed space and let little x be in X. Well, and let phi be in X star. There's at least one thing in X star, namely the zero functional. So there's at least one continuous linear functional. But at the moment, we don't really know. You haven't got much of a handle on if it's a pretty weird abstract normed space. How do you know there's any interesting bounded linear functionals at all? Well, that comes from the Hahn-Banach theorem, and it uses Zorn's lemma and the axiom of choice and all that. How big can mod 5x be? Well, suppose that norm, obviously it can be as big as you like if you can get a non-zero value, but suppose that the operator norm of phi is smaller or equal to 1, then you'll get that the modulus of phi of x is smaller or equal to norm of x. And one important consequence of the Hahn-Banach theorem is that there exists a phi in X star with norm phi less than or equal to 1 and phi of x equals mod x. No, norm x, sorry. Why have I said operator norm less than or equal to 1? This is a bit silly. Normally you would say operator norm equal to 1, but there is a slight problem. X could be the zero norm space. And then X star is also the zero norm space. And then you can't have an operator, all the phis have got operator norm 0. That's rather boring. If X is not equal to 0, so if little x is not equal to 0, then this phi will have operator norm equal to 1, and it's what you call a support functional for x. So the existence of these is non-trivial, not obvious, and it's a consequence of the Hahn-Banach theorem. But the idea is that you start with your non-zero x and you try to do as well as you can with a linear functional whose norm is 1. It's not obvious there are any at all. Hahn-Banach theorem will provide you with some, and it'll even better, it'll provide you with a linear functional whose operator norm is 1 and which is as big as it possibly can be at x. And it's in view of that are what we call the natural embedding from x into x double star defined by x goes to x hat, where x hat of a linear functional is phi of x, really is an isometric linear embedding. Okay, so we'll talk more about that next time. But we'll stop there for today. Ah, yes, and next time is tomorrow morning at 11. Because I've booked these extra slots now, and I can confirm that we'll be in C4 at 11 o'clock tomorrow morning.